Patil Rajale Arts, Science, Commerce College, Adinathnagar, Taluka Pathardi, District-Ahmednagar, Department of Chemistry and Internal Quality Assurance Cell organized national level webinar on HPLC technique in pharmaceutical and chemical industries will be discussed. So on the behalf of Dadapatil Rajale, Arts, Science and Commerce College, Department of Chemistry and Internal Quality Assurance Cell, and I, Sushma Ekshinde, welcome to all of you dignitaries present on the screen and off the screen. Very good morning all of you. The principal of the college, Dr. R.J. Temkar sir, and today's resource person, Professor Dr. Dnyaneshwar R. Shinde, Department of Chemistry, Professor Ramkrishna More College, Akurdi, Pune, who has organized this one-day national level webinar HPLC technique in pharmaceutical and chemical industries, Dr. Sadhna Mhaske and Dr. Nirmala Kakade, head of the Department Chemistry. All my faculty members and all my participants and all my students, on behalf of Dadapatil Rajale College, I first welcome to all of you. Dadapatil Rajale Arts, Science and Commerce College has been established by Honorable late Dadapatil Rajale alias Bhau in 1991. The college is located in rural area. Majority of the population of the given region works at sugarcane cutters. The vision of the college is to impart knowledge and skill in rural youth for the creating strong human resources needed in a nation building. The college is dedicated to provide education for all with its missions to bring deprived section into mainstream of higher education. To accomplish its mission, the stakeholders of the college we have taken a great efforts right from the campus developments to the student satisfaction. The colleges provides learner-centric atmosphere with the help of ICT-based resources, then well equipment, library and laboratory, gymnasium and indoor and outdoor stadium, competitive examination guidance center and NSS unit of the college invert various activities of the college and outreach program. The college has offered various courses for students. It has offered 5 academic programs in the science stream and post-graduation in analytical and inorganic chemistry and 6 programs in arts stream as well as commerce stream. Today's webinar is HPLC technique, and HPLC technique is very useful technique in pharmaceutical and chemical analysis. So again, I welcome to all of you, all the participants and resource person. I quite sure and from today webinar will be helpful to the student and faculty. Then again I welcome to all of you and thank you. Thank you so much, sir. Now I request to Dr. Sadhna Mhaske, Head of Chemistry Department, to introduce our resource person, Dr. Professor Dnyaneshwar Shinde, sir.
Hello, good morning all. First of all, I am very much thankful to our patron, management and principal, Dr. R.J. Temkar sir, to arrange this webinar. On this occasion, I welcome our today's resource person, Dr. Shinde sir, and you all who are on the screen and off the screen. On the behalf of Department of Chemistry and IQAC of Dadapatil Rajale, Arts, Commerce and Science College Adinathnagar, Taluka Pathardi. Before going to say anything about the topic, I have a sad news for all of us yesterday. We have lost Professor Vasantrao Fatke, Head Department of Chemistry of Sonai College. I, on the behalf of all of us, pray tribute to our colleague, Professor Fatke. May his soul rest in peace. Friends, we know that chemistry is related to chemicals, chemical bondings, chemical reactions, synthesis, and instrumentation. In chemical industries, instrumentation is important in production, quality control, quality assurance. HPLC is the technique which play key role in chemical and pharmaceutical industries. To deal with this topic, we have one of the expertists working in this field tirelessly. Actually, he doesn't need any introduction. Chemistry fraternity know him one or other way. I consider myself fortunate to have an opportunity to introduce such a great scholar to you. Let me start on his academic profile. He is none other than Dr. Dnyaneshwar Shinde. Dr. Dnyaneshwar Shinde is working as professor in Professor Ramkrishna More College, Akurdi, Pune. He has 27-year experience of teaching. His area of research is nanomaterial synthesis. He has published 23 papers in national and international journals. He has a resource person for national and state level conferences. He has presented many papers in international conferences. He is a research guide and guided students for MPhil and PhD. Sir, I request you on this occasion to guide us on the topic that HPLC techniques in chemical and pharmaceutical industries. Thank you. Thank you very much.
Honorable Principal, Dadapatil Rajale College, Adinathnagar. Honorable Head of the Department, Chemistry, Dadapatil Rajale College, Adinathnagar. All the colleagues and the teachers and the professors of the college and the students. Today's topic for the discussion is high performance liquid chromatography in the pharmaceutical and the chemical analysis. Before coming in the teaching, I have worked 2 years in the industry, and at that time I have handled the HPLC. In our college, we have purchased the HPLC system from in 2008, and from that time I am using the HPLC system. So we'll start without wasting much more time. I will start with the topic. Okay. So if you see the chemical methods or the methods of analysis, there are many methods of chemical analysis, and there is continuous addition of the methods of analysis. Okay. So there is a question. There are many methods for the analysis of one substance. For example, if you take on the aspirin, you can analyze by volumetry, you can analyze by spectrophotometry, you can analyze by HPLC, even you can analyze by the HPTLC, or by using the electrochemical technique also. The question is that why there is such a vast development in the instrumental methods of the chemical analysis. So there is a need of human civilization or the lifestyle. Our lifestyle is continuously progressing, and we need the different types of the substances, and one of the important type of substances we need is the medicines. We use many medicines in our life, okay, and if you see any medicine that reach to you, okay, that reach to you has to pass many tests. It is tested for the purity, and for the determination of the purity we require the methods, okay, variety of methods they are required for the purity analysis, okay. Now, why the purity of the medicinal compounds? Even there is a very small amount of the toxic substance present in the medicine that gives rise the many side effects. So the purity of the medicine or the pharmaceutical compound is tested before any of the pharmaceutical compound reaches to you. Okay, now what are the classical method? And we go just 70 years back. So just the time of Second World War. So whatever the technique we are using at UG and PG laboratory today, they are used for the testing of the pharmaceuticals or the medicinal compound. Okay, and what are the technique we are using in the laboratory? We are using in the laboratory the technique like TLC, okay, thin layer chromatography, melting point, okay. These are the technique we are using, melting point and the TLC. If we get the single spot on the TLC, melting point match with the reported melting point, then we are saying the substance is pure, okay. Do this much is sufficient? Do these two tests are sufficient? No, these two tests are not sufficient. And I will take the very simple example, paracetamol or acetaminophen. So if you see the paracetamol or acetaminophen, okay, it is antipyretic and the analgesic substance. Okay, antipyretic and the analgesic substance, and it is used 100 years back. Okay, discovery is 100 years back, and till today it is used in the treatment of the patient, okay, and till today it is much more useful. If you see the many medicines they come in the market, and after some time they disappear from the market. But if you see aspirin and the paracetamol, these are the two drug substances known long back, and till today they are in the market. In fact, if you see aspirin is having the highest production worldwide, and after aspirin the paracetamol is the second drug which is used in the treatment of the patient and having second position in the production worldwide. Okay, so if you see the okay, so I will skip this slide. Okay, what are the impurities that may be present in the paracetamol? Okay, what are the impurities that may be present in the paracetamol? Ultimately, we have to think of route of synthesis, how it is synthesized, how paracetamol is synthesized, and if we know the synthesis procedure, what are the chemicals used for the synthesis of the paracetamol, okay, you can find out the impurities. Okay, so the first route, the benzene is taken, okay, benzene, the chlorination of benzene is carried out, we get the chlorobenzene as a first product, the nitration is carried out, okay, nitration is carried out, we get the paranitrobenzene, or the para-nitrochlorobenzene. Okay, then the reaction NaOH is added, the reaction is carried out, chloride is substituted by the hydroxyl group. Okay, so we get para-nitrophenol. Okay, so para-nitrophenol, we have this para-nitrophenol. Okay, the reduction is carried out, nitro group is converted to the NH2 group, and we get para-aminophenol. And lastly, acylation is carried out, or N acylation is carried out, and when N acylation is carried out, we get paracetamol or acetaminophene. Okay, acetaminophen. Okay, so if you say we require benzene, the chlorobenzene, para-nitrochlorobenzene, para-nitrophenol, and para-aminophenol, these are the intermediate. So how many intermediate? If you label intermediate, 1, 2nd, 3rd, and the 4th, and 1 is the starting material. Okay, so starting material is liquid. Starting material is liquid. But if you see one, even chlorobenzene is also liquid. But if you see 2nd, 3rd, and the 4th, they are solids. So liquids can be easily given out in the purification process, or they may be present in the adsorb form. But though crystallization is carried out, small quantities of the solids such as para-nitrochlorobenzene, para-nitrophenol, and the para-aminophenol, they may be present as impurities in the paracetamol. Okay. So what research says? Research says that para-nitrophenol, okay, we have the para-nitrophenol, we have para-nitrochlorophenol, 4-chloroacetamide, para-aminophenol, hydroquinone, and 1,4-benzoquinone. These are the 6 impurities they are identified. So one can ask the question, from where hydroquinone come, 1,4-hydrobenzoquinone come. Okay, so if you see, these are the side products. They are not expected, but they are found. So if you see, these are the 6 potential impurities. They are present in the paracetamol. Okay. Now, if you taken the classical method that is used for the purity determination, it is the titration of the paracetamol, with ceric ammonium nitrate. If you see this impurity, they are present less than 1%. They are present in the amount less than 1%. Okay, and we are using here volumetric method, that is the recommended method in the Indian pharmacopoeia. Okay, volumetric method, titration with ceric ammonium nitrate. Though these impurities are present, they do not react with ceric ammonium nitrate, and the percent of these impurities is very low. So though they are present, they do not reflected in the quantitative analysis. The another technique we are using is the thin layer chromatography, TLC. As percent of impurity is less than 1%, though they are present, they do not appear on the TLC. The spot of this compound do not appear on the TLC. Now the question is that if they are present less than 1%, what will happen if they are present? Ultimately, all these are toxic in nature, and some of the compound, they are present in the ppm level or the ppb level, they show toxicity. They show toxicity. So we have to worry about these impurities. Okay. So whatever the classical methods of analysis are there, they are very, very less sensitive, and hence we need the sensitive methods of analysis. And that's why there is a development in the analytical science, in the analytical chemistry, and new methods of analysis are continuously added. And one of the techniques they are added, the chromatographic instrumental methods, and GC and HPLC, they are added. Okay. So if you see the HPLC technique, it is introduced in the 1954, and the technique is so important that the Nobel Prize was awarded to the technique. Okay, so this is the Nobel Prize winner technique. And why we take care of, why we discuss Nobel Prize? Okay, since the technique which is very, very useful, the discovery which is very, very useful for welfare of human being, for that discovery Nobel Prize was awarded. So the point is that the HPLC is one of the very, very important technique in the analytical science. And now we will start with the APC tablet. Okay, the HPLC analysis, the technique, and how the aspirin, paracetamol, and the caffeine tablet is analyzed. This is one of the oldest experiment done in the pharmaceutical analysis, and till today these tablets are in use and analyzed by the HPLC technique. Okay. So if you see the APC tablet, there is aspirin, paracetamol, and caffeine. Three components. So if you use the classical method, what will happen? If you use classical method, we have to separate aspirin, paracetamol, and caffeine. So we will have to separate by using the suitable solvent extraction method, or whatever the method classically we are using for the separation. And then we have to analyze one substance at a time, or we have to devise a method where the reaction takes place only with aspirin and paracetamol and caffeine remains inactive. Then second titration, paracetamol. Third method, caffeine. But if you see the classical method, volumetric method, or the spectrophotometric method, it is very, very difficult to analyze one substance at a time by using the classical method. That's why the high performance liquid chromatographic method is introduced for the analysis of such complex substances. Okay, so when we are saying the HPLC, high performance liquid chromatography, what are the components? Okay, my voice is clear? Can anybody? My voice is clear? Hello? Hello? कोणीतरी फीडबॅक द्या. Hello?
हाँ सर.
Voice is clear?
हॅलो.
आवाज येतोय का क्लिअर?
हो येतोय सर.
हाँ ठीक है. I have to just confirm. So when we are saying the HPLC, What are the components? Solvent reservoir, pump, injection port, column, detector, and the output device. We will discuss this component one by one. Okay, one by one. So if you see the solvent reservoir, simply it is glass bottle. Okay, solvent reservoir. It is the glass bottle of 1 liter capacity. So Teflon tubing. There are two Teflon tubing. One is for bubbling of the neon gas or the nitrogen gas, and another is to pump the liquid. Okay, to pump the liquid. Now, what are the care that is taken? So, what is the mobile phase? It is the solvent used for the experiment. It may be methanol, it may be acetonitrile, it may be acetone, it may be N-hexane. Okay, any of the solvent that is used for the HPLC experiment, it is called as a mobile phase. So, two important things regarding the mobile phase. The mobile phase must be degasified. Okay, the degasification must be carried out, and the mobile phase must be filtered properly. Mobile phase should not consist of any particulate matter. Okay, and it should be degasified. Why the degasification? Any of the liquid that may consist of the dissolved gases, and when the pumping of mobile phase is carried out, it is carried out at high pressure, and when high pressure is applied, the dissolved gas form the bubble, and that bubble may be trapped in the column, and it causes the it causes the stationary phase of the column to be disturbed, or it affects the separation. So what is done? The sonication is done, the sonicator is used, and mobile phase is sonicated nearly for the 10 minutes, and then the neon gas or the nitrogen gas is bubbled, or the neon atmosphere is maintained in the bottle. Why the neon atmosphere? Neon is not soluble, or argon is not soluble, nitrogen is not soluble in the solvents. Okay, so to avoid dissolution atmospheric gases, this care is taken. The second important part is the pump. So if you see in the HPLC, there are the variety of pumps, and we will discuss only one type. Okay, so if you see in the pump, it must be resistant to the corrosion. Okay, it must be resistant to the corrosion. One thing, since we are using the liquid or the solvent, they may react, and if corrosion takes place, the pump will not work well. So whatever the pump material, it must be corrosion resistance. Pumping must be pulse free. Okay, whatever the pumping of liquids is there, it must be pulse free, that it must be continuous. Then the mobile phase rate. Okay, so we are pumping the mobile phase, and that rate of mobile phase must be adjustable. What it means? That it means that we can adjust 1 ml per minute, we can adjust 2 ml per minute, we can adjust 1.5 ml per minute, and the pump must be easily repairable. Okay, pump must be easily repairable. These are the requirements. Okay, now there are variety of the pumps, and I will discuss only the twin-headed pump that is used in most of the HPLC systems today. So I have shown the twin-headed pump here. Okay, the very first is the solvent reservoir here. This is the solvent reservoir. Then the cylinder, here you can see the cylinder, this yellow one. This is the cylinder. Okay, second one is the cylinder. The third one is the moving pistons. Okay, you can see the one piston here, one piston here. These are the two pistons. Okay, then here these are the valve system. One valve, second valve, third valve, and the fourth valve. There are four valves. Okay, at the center we have motor driven eccentric cam. This is called as a motor driven eccentric cam, and with the help of this eccentric cam we pump the mobile phase. Whatever the pistons are there, they are moved left and right continuously within the cylinder, and this movement is done by using the electric motor and the eccentric cam. Okay, how it is working. Okay, you can see this piston is there. Okay, these are the two pistons, and I will show the first stroke. In the first stroke you can see that, okay, it is moving in the left hand side. Okay, these both blue pistons will move in the left hand side. Eccentric cam is moving. Okay, so this is the first stroke. What will happen within this first stroke? This will open, this valve will open, this valve will close, this valve is closed, and this is open. So these two cross valves, 1 and 2, it is open, and these two cross valve, 3 and 4, they are closed. Under this condition, what is happening? The solvent moves in this direction into this cylinder. Okay, so the solvent moves like this. Okay, just I will remove some of the part. Okay, so once again just see. So piston is moving in the left hand side. Solvent moves from the reservoir into the left cylinder, and from right cylinder it is passing to the column. Okay, so the direction of the movement of the solvent is like this. This cylinder is filled, and from this cylinder it is passing to the column. Next stroke on the left hand side. First stroke right hand side, next stroke left hand side. What is happening? Solvent moves like this. So this piston is filled, this piston is filled with the solvent, and from this piston solvent is passed to the column. So this piston continuously moves left and right, and by this way the mobile phase is continuously pumped to the column. Okay, here you can see the total action together. Okay, you can see the movement of the piston left and right. Okay, left and right. Okay, so there is a problem with the internet, is slow, I think, so you cannot see the action properly, but eccentric cam is moving, and due to this the piston is moving left and right. Okay, piston is moving left and right, and mobile phase is passed to the column. Okay, so the visualization is not quite clear, the problem is there. Okay, but if you see the PowerPoint, it is working very well on my laptop, but the broadcast problem is there. Okay, okay, so this is the pump, and this is called as a twin headed reciprocating pump. The pumping is pulse free, and constant volume is pumped. Okay, Then the high pressure gradient, low pressure gradient, I will skip this part since this will require actual handling. Okay, the sample valve and loop system. Sample valve and loop system. Okay, we have to introduce definite quantity of the sample at the head of column. Okay, so whatever the square part you can see, okay, this square part you can see, this part, it is called as a sample loop. Whatever the dotted circle, it is the valve which can be rotated. These are the internal connections. These are the internal connection. Now, the mobile phase is passing from this point. Mobile phase is passing from this point like this to the column. So at that time, you can see that you can fill up sample from this end. You have to inject sample from this end. This loop will be filled like this, and excess of sample will come out. Excess of sample will come out. So when mobile phase is passing to the column, you can fill loop independently. Once loop is filled, you can load the sample on the column. Okay, this is already I have shown. Okay, now you can rotate the sample valve. You can rotate the sample valve. And when sample valve is rotated, what is happening? What is happening? Mobile phase is passing from this point, and at this point, it is connected to the sample loop. So mobile phase will pass like this. Like this. To the column. So whatever the sample inside the loop is there, this sample is loaded on the column head. Okay, loaded on the column head. So when the valve is rotated, when valve is rotated in the left hand direction, what is happening? This connection, whatever the connection here is there, it is shifted here. The connection is shifted here, and this connection is shifted here. So there are three internal connections. I will show on the back slide. Okay, these connections are shifted like this. One position ahead when we rotate this valve in this direction. Okay, so you can load sample from the column, loop on the column. Okay, so the column. So if you've seen the analytical column, it is of 25 centimeter length. Okay, internal diameter 4.6 mm, and particle size about 5 micron. These are the three important characteristics of analytical column. Apart from analytical column, in market variety of columns are available. But when we are saying of a standard analytical column, which is mostly used for analytical purpose, other columns, they are mostly used for the separation purpose, identification purpose, etc. But the analytical column is very typical, and universally it has 25 centimeter length, 4.6 mm diameter, and the particle size is very small. Very densely packed column is there of 5 micron. Okay, so if you see these two sides here, we have a stainless steel filters. Then these are the nut and bolts which are packed here, so that column can be connected on one side to the mobile page and on another side to the detector. Okay, so we have the column, analytical column, and there are variety of stationary phases are available. Okay, so if you see, the oldest one is the silica gel. Then even activated charcoal, it is also tried. Then we have silica coated with liquid, highly viscous liquids, okay, such as polysilicons or the silicon oil. Okay, it is coated and they are used. And after this, the breakthrough is there, and we have the C18 column. So if you see the C18 column, we have silica gel. The reaction is carried out. We have C17 or C18 H37 is there. Okay, so on a silica gel, okay, the reaction is carried out, and this long chain C18 H37 molecule is attached to this oxygen. Okay, so we have alkane group C18 H37. So we have the name is C18. So what is the characteristic? If you see the silica gel, SiO2 or SiOH, it consists of the hydroxyl group. When hydroxyl group is there, it is silica gel. It is polar. Surface is polar in nature. And if you see this group C18H37, it is non-polar in nature. So in chromatography, when stationary phase is polar, it is called as a normal phase. And when stationary phase is non-polar, it is called as a reverse phase. So the C18 column is always referred as RPC18. Reverse phase C18. Reverse phase means your stationary phase is non-polar in nature, and you can use very polar solvent like water, acetonitrile, methanol. If you see the silica gel, SiO2 or the silica gel, you cannot use polar solvent like methanol, acetonitrile, water for the separation. And many of the pharmaceutical compounds, they are soluble in methanol, acetonitrile, even in water. And if silica gel is there, these pharmaceutical compounds cannot be analyzed, cannot be separated. And that's why the requirement is there. We should have the non-polar column so that we can use the very polar solvent or the mobile phases, so that variety of compound can be analyzed. And that's why the columns such as the C18 or the C8, okay, C18 or the C8 is introduced. Okay, then detectors. Okay, so we have UV visible multi-wavelength detector. Okay, this is the most common type of the detector available today. If you see in the old reference book, you will get in the UV visible the dual detector or the dual wavelength detector, single wavelength detector. These detectors are the outdated. Okay, today mostly UV visible multi-wavelength detector. In other words, the UV visible spectrophotometer is used as a detector. UV visible spectrophotometer is used as a detector. So if you see this detector, the source of radiation is there, and it is the lamp. It is there are the two lamps. One is the deuterium lamp, which work in the region 200 to 330 nanometer, and we have the tungsten filament lamp, which works from 330 to 800 nanometer. So we have the source of radiation. Then we have the monochromator From 200 to 800, we have to select the single wavelength, and the diffraction grating used as a monochromator. The reflecting planes are mirrors are there. The cell is there. What is the cell? From column, mobile phase passes into this, and from this point it come out, and from this point the electromagnetic radiation passing from the cell, and we record the absorbance. Okay, the sample cell, the sample out, the detector, the output device. Okay, so I will just remove the markings. Okay, when we put the the lamp on, what will happen? We get the radiations of all wavelength, and here in between you can see the concave mirror. It acts as a reflector, and it reflects the radiation on the monochromator. So you can see we have put the lamp on, and the radiations are passing. Yeah, the action is quite fast, so it is not appearing. Okay, you can see now. Okay, animation is not looking properly on your screen, or yes. Okay, so I will go back, and instead of showing animation, I will show with the help of pen. So that you can understand well. Okay, so radiation will pass like this. They will pass on the monochromator, and from monochromator you will get the monochromatic radiation of the single wavelength. They will pass on this mirror. They will pass through the cell over the detector. Okay, so here whatever the mobile phase is there in the cell, its absorbance is continuously monitored with time. The detector, the signal is processed by using the computer. Okay, and you will get the chromatogram. So I will not discuss the fluorescence detector. Okay, now how the HPLC instrument work? So you can see the whole equipment here. Pump is there, and very first we have to start the pump. Okay, so I have started the pump, and as pump is started, mobile phase is passing to the column. So here we have the pump is there. Okay, column is there. Here we have column. Okay, here we have the sample injection system. Here we have the detector, and here we have the output device, that is the computer. Pump is working. Okay, now what is the second point? We have to inject the sample. So we have to second point, we have to start the detector. Okay, so detector is started. The radiations are passing through the cell. Third point, we have to inject the sample. Okay, we have to inject the sample. We have a syringe here. Okay, you can see the syringe here. Okay, and from this point, we have to inject the sample. Okay, sample is injected. Okay, sample is injected. Now we have to rotate this valve. You can see the valve is there. Okay, this is the valve. I will rotate this valve. When valve is rotated, sample will injected on this column, and you can see, okay, you have to look at this part. The components are moving down. Components are moving down. So you have to concentrate on the column. You have to concentrate on this portion, and here also on this screen also. Okay, we have to look at these two parts. Okay, so I will load the sample. Okay, you can see the components are moving, and here the chromatogram is recorded. The components are moving and chromatogram is recorded. The yellow component is moving in the detector. You will get the one peak here. The red component will enter into the detector. You will get the second peak. Okay, so what is the process when we load the sample on the column? What is happening? The sample passes through the column and it gets separated into the two components. Okay, there are mixture is of two components, and as soon as component enters into the detector, you will get the peak. Why? Since your sample is absorbing the radiation. For example, I am analyzing the aspirin. I will use the paracetamol or the caffeine. So I will use the wavelength around 260 nanometer. This is the wavelength at which paracetamol, aspirin, and caffeine all have the absorbers. Okay, so once again, see the process. I have loaded the sample. Components are moving, and when they are moving, they get separated from each other. When yellow component will enter, you will get the one peak. Yes, first peak is appear, and this is the actual process. When you run the HPLC experiment, similar thing happens. So I have animated for that. Second is entered into the detector, we will get the second peak. Okay, so when we perform the HPLC experiment, what is the output we get? Output we get is the chromatogram. We get the chromatogram. Okay, so what are the characteristics of the chromatogram? So I will show with the help of the diagram. Okay, so this is the chromatogram. So in the chromatogram, what is the x-axis? X-axis is the time. X-axis is the time, and y-axis is the detector response. Detector response. As such, it is absorbance, but expressed in the unit usually millivolt. Usually millivolt. Okay. If other types of detector are there, we have not discussed all types of the detector. Coulometric detector is there, conductometric detector is there. Then instead of millivolt, it is microampere. So y-axis detector response may be millivolt or it may be the microampere, and the x-axis is the time. From where time is counted? From what point? at the point of injection of sample, the time is counted. Okay. Now, this is the time. Okay. At this point, 0 minute is there. What it means that at this point we have injected the sample and the first sample get detected. What it means that it is come out from the column. Okay, so retention time is nothing but it is the time which is spent by the component in the column. Okay, so retention time for first, then retention time for the second, PR1 and the PR2. Okay, retention time of the two components is different. Why? Since they are adsorbed. Adsorption is the process. The first component is adsorbed to the less extent, hence retardation of the first component is less and hence it come out first. The component 2 is adsorbed to the greater extent. Okay, component 2 is adsorbed to the greater extent, hence it moves slowly through the column and it spent more time in the column and hence it come out later. Sorry, the first thing, retention time. Now, the quantitative factors, what we are using for the quantitative analysis. The peak height and the peak area, these are the two important parameters which are related to the quantity of the substance. Okay, so how they are determined? So if you see peak is triangular in nature, the peak is triangular in nature. So if you consider peak as a triangle, then whatever here I have shown, this is nothing but the width of the peak. Base of triangle is nothing but the width of the peak indicated by W. This is the height of triangle indicated by H. It is the height of peak. It is the height of peak. So if you see in the time such as 1990, we have to carry out analysis of chromatogram manually. Today computer systems are there, so we have to not worry about the determination of width and the height. But you should know how it is calculated. So we know width and the height. Then the width at the half height. Width of the peak at half height. At h by 2, it is determined. Okay, now h is height and it is expressed in the unit millivolt. We know W, we know H, then what is area? 1/2 W into height. Half of base into height is the area of the triangle. Okay, area of the triangle. So, what is done? Width at half height into height of the peak, that gives rise area of the peak. So area of peak is directly proportional to the concentration, or the height of the peak is directly proportional to the concentration. So this is the basis of quantitative analysis by using Hplc. So chromatogram is output and we can use the chromatogram for the determination of the quantity of the substance. So once chromatogram is there, we should know accurately area and the height. Now why the height at width at half height, width at half height. I will just remove some of the part, just a minute. So if you see the actual chromatogram, there are many problems. It is not too simple. Okay, it is not too simple when we deal with the actual experiment. So if you see the actual thing, you will get the peak like this. Okay, so somebody will take tangent like this and will determine this as a half height. Some will put tangent like this, and this will take as a width of the peak. So person to person, as peak is not actually triangular, practical cases, but if you see at half height, at this point, there is no problem. So to avoid errors in the determination of the width is determined at half height. Okay, at the base it is very difficult since variety of types of the baselines we may get. We may get the baseline sometimes like this. Okay, sometimes you get like this. Okay, so peak shapes are variety, and when peak shapes are variety, it is very difficult to determine width at the base, but it is simple, no error when width is determined at half height. So usually when we determine the area, width at half height is recorded. Okay, so quantitative analysis using HPLC. So this is the impure paracetamol. Impure paracetamol. So how many peaks you can see? You can see the 6 peaks. This is the actual experimental chromatogram. The peak number 2, this peak is having the highest height. So it is a paracetamol. It is the main substance. Then how you will identify peak 1, peak 2, peak 4, peak 5, and peak 6. So the very first thing, if paracetamol is pure, you will get single peak. As there are 6 peaks, there are 5 impurities. So what is our conclusion looking at the chromatogram or the HPLC chromatogram? Okay, looking at HPLC chromatogram, the substance is not pure as there are many peaks, there are impurities. Peak number 2 is definitely of acetaminophenol since it is the highest peak. Okay, peak height is very high, so it is the main substance, and the other peaks are having very low height, hence they may be present in the small amount. It means that they are the impurities. So there are 5 impurities in the paracetamol. If TLC is there, these other 5 substances may not be visible. So how you can identify the impurity peak? So when we have discussed the method of synthesis of the paracetamol, we have discussed that these 6 impurities: hydroquinone, parabenzoquinone, 4-aminophenol, 4-nitrophenol, and 4-chloroacetaniline. These are the impurities, they may be present. Okay, so we have to screen this chromatogram for the presence of these substances. So what I have done, I have taken pure parabenzoquinone and I have run the chromatogram. I have run the chromatogram. So you can see the retention time of parabenzoquinone match with this peak. So this peak is of parabenzoquinone. Then 1-hydroquinone. So the peak is appeared here, and if you see the retention time of these match with this, so this peak, okay, this peak is of hydroquinone, 1-hydroquinone. Then 4-aminophenol, the peak is at this point, it matches the retention time with this, so this peak is of the 4-aminophenol. 4-nitrophenol, you can see the peak is here, and the retention time, it matches with these. So this peak is of 4-nitrophenol. And the last one, 4-chloroacetaniline. Okay, this last peak of 4-chloroacetaniline. So this is the qualitative analysis. This is the qualitative analysis. We have identified the impurities that are present. So what we should have to identify? We should have the idea what impurities may be present. If you don't have idea what impurities may be present, you cannot identify the impurity. You can just say the impurity is present, but you cannot identify the impurity. Okay, this is the thing. So we should have the standards of, and we have the standard of each impurity. We have run the chromatogram of impure paracetamol and the chromatogram of each impurity in the pure form, and from retention time we have identified the peaks. So retention time is the qualitative factor for identification of the substances that may be present in the sample. Okay, the next is quantitative analysis. And we are taking the example of paracetamol, aspirin and caffeine tablet. Okay, so if you see the aspirin, it is analgesic, antipyretic, paracetamol analgesic, antipyretic, and the caffeine is not analgesic or antipyretic. But this aspirin, paracetamol and caffeine, these tablets are the most common, and today mostly paracetamol and the caffeine such as a crocin, okay, crocin tablet. If you see the paracetamol, the analgesic effect such as on headache is very less. But when caffeine is added, the effect of the paracetamol and caffeine on the headache is very good, and a headache stop within half an hour. If only paracetamol is taken, the headache do not stop or it require much more time. So many substances in the pharmaceutical, they are mixed together to improve the action of one or more drugs. Okay, so aspirin tablet is there. So what we have to do? First upon, we have to run the Hplc chromatogram for the tablet, and this is the Hplc chromatogram for the tablet. We are getting 3 peaks. You are getting 3 peaks. Can you identify first peak, second peak, and third peak? It is of which? It is of aspirin, paracetamol, or caffeine? No, you cannot identify looking at the chromatogram. And if you don't know which peak belong to the which material, you cannot carry out quantitative analysis. So when you have to do quantitative analysis, first upon you have to identify the peak. So ultimately, we have to run the chromatogram of the pure substances. So I have a chromatogram of pure caffeine, chromatogram of pure paracetamol and the chromatogram of pure aspirin. Okay, so we get the single peak in caffeine, paracetamol and aspirin, and such a standard they are available in the market. Highly pure samples are available, and according to the GLP, okay, good laboratory practices, okay, you don't have, but it is one of the practice in the industry, good laboratory practices. And when we have the good laboratory practice, the certified standards are used. You are saying that I have prepared the caffeine, I have purified it number of times. No, you cannot use it as a standard. It should be the certified standard. And certified standards are provided by certain laboratories only, which are accredited, identified. Accredited means identified, and the permission is given by the government of India or the Food and Drugs Administration of the India. Such a certified samples are provided by the laboratories, and they must be used for the analysis. Whatever the procedure used, it is approved, accredited, and approved by the Food and Drugs Administration, and such a procedure is used only. So whatever the mobile phase is there, pumping rate is there, detector wavelength is there, condition is there, buffers are there, all they are fixed, and all they are in the method development and the validation. So well developed method and the validated method is used for the HPLC analysis. Then and then the analysis is performed. So first of all, we have to identify. So you can see this peak, the central peak is of caffeine. So I will write down C here, caffeine. This first peak is of paracetamol, and the third peak belongs to the aspirin A. So we have run the chromatogram of the tablet. We have run the chromatogram of caffeine, paracetamol and aspirin under identical condition, and we have identified peaks in the chromatogram. Okay. Then what information you will get from the HPLC chromatogram? Okay, you can see the one large table is there that is generated by computer software automatically. Computer software generate whatever the table you can see automatically. So retention time, I have taken only 3 parameters: retention time, peak height and the peak area. Retention time, peak height and the peak area. This is the information directly you will get in the tabular form when you use the computer software. Just you have to click on the chromatogram and you have to analyze. When you say analyze, you will get the table, and in the table many other informations are there. Percent area is there, percent height is there, but I have extracted only 3 important points: retention time, peak height and the peak area. So this is for tablet, this is for paracetamol, this is for caffeine, and this is for aspirin. So the first peak at 2.11 minute, it is of paracetamol. Okay. The second peak at 2.93 minute, it is of caffeine, and the third peak at 5.15 minute, it is of aspirin. So we have compared retention time 2.11, 2.11, so it is paracetamol, 2.93, 2.93, so it is a caffeine, and 5.15, 5.14 here. Small changes there. Such a small changes, they may take place in the retention time, since there is a power fluctuation. Okay, power fluctuation, and ultimately it is the physical process. The absorption is the physical process. So the small variation, it can be accounted. Then what we get? We get peak height and peak area for each sample and standard. Okay. Now, what could be done with this information? With this information, you can carry out quantitative analysis. You can carry out quantitative analysis. Okay. So how quantitative analysis can be carried out? So calculations. Okay. So we have peak height is directly proportional to the concentration, or peak area is directly proportional to the concentration. We have to use these two parameters. So how it can be correlated? Concentration of sample upon concentration of standard is equal to peak height of sample upon peak height of standard. Therefore, concentration of sample is equal to peak height of sample upon peak height of standard into concentration of standard. Okay, so whatever we have done the caffeine, solution of caffeine, paracetamol and aspirin, usually concentration required is very low. The caffeine is used at 0.02 milligram per ml, very small quantity. Paracetamol 0.01 milligram per ml, aspirin 0.01 milligram per ml. Okay, these are the concentration that are used for the analysis. Mobile phase is methanol 90%, 10% acetonitrile containing 0.5 ml acetic acid. Okay, so you can put up peak height of sample, peak height of standard, concentration of standard, whatever the quantity you will get milligram per ml. Now suppose your sample we have prepared 25 milligram tablet dissolving in 100 ml. From that 1 ml is pipetted and again diluted for 25 ml, and this is used for analysis. This is used for the analysis. So you will get what is the unit? Milligram per ml. So you will get suppose x milligram per ml. Here what you have to do? X multiplied by 25. X multiplied by 25. You will get milligrams, say y milligram in 25 ml. Y milligram in 25 ml, that means that they are present in the 1 ml. So 1 ml is equal to y milligram. 1 ml is taken from 100 ml. So 1 into 100, you will get milligram in 100 ml, and this 100 ml is prepared from the 25 milligram tablet sample. So suppose here we take Z milligram. This 1 into 100, you will get Z milligram. So 25 milligram is equal to Z milligram, say aspirin. Like this you can calculate the milligrams in the milligrams of caffeine, milligrams of the aspirin also. Okay, so you can use peak height or the peak area. Now I will erase this. Now, if peak area is there, okay, C sample upon C standard is equal to A sample upon A standard. Therefore, C sample is equal to what? A sample upon A standard into C standard into dilution factor. So whatever this X into 25 into 100, this part is there that contribute for the dilution factor. So this is called as a comparative method. This is called as a comparative method. Why comparative method? Whatever quantitative parameter there is, area of sample or the height of sample, we are comparing with standard. Without standard, this analysis is not possible. Absolute analysis, it is possible only in GC. HPLC, absolute analysis is not possible. So we compare the concentration of standard and area of standard with the concentration of sample, and by that way we are obtaining concentration of sample, and hence it is called as the comparative method. Okay, now second, this method is not too accurate. When we want accurate analysis, we have to go to the another method, and that is the calibration curve method. Okay, calibration curve method. In brief, I will explain the calibration curve method. So what is done in the calibration curve method? We require 4 to 5 standard. It is the time consuming. Okay, it is time consuming, but we require 4 to 5 standard of each of the component. For example, we have to analyze aspirin, caffeine, and the paracetamol. We require 5 standard of the aspirin. We require 5 standard of the caffeine. We require 5 standard of the paracetamol. Okay, so what is done? So I will take an example of paracetamol. So we have to prepare the paracetamol sample, say point not 2 milligram per ml, not 5 I will take, then 0.1, 0.015, 0.02, 0.025. Okay, so we have 5 standard. We have to run chromatogram for each of the standard, and we have to find out, say, area. Mostly area is used for the calculation, height is not used. So area, suppose we have run the 5 chromatogram, we have run the chromatogram for the sample also, and here you will get, say, 88, three 71, and lastly 449. We get the area of the sample like this. Okay, area of the sample like this. Standard. So what you have to do? We have to plot the graph. We have to plot the graph. Concentration of standard, and here area. So you will get the graph, and we have to plot a graph passing through the origin. We have to plot the graph passing through origin. So we get calibration curve. Now we have an area of sample. Suppose it is 330. So here is the value, say 330. We have to put up the perpendicular and extend to the concentration axis. You will get sample here. Okay, so whatever your unit is there, if milligram per ml is there, you will get the concentration of standard milligram per ml. If it is microgram, you will get the unit. So whatever the unit of concentration we are using, same unit will be applicable for the concentration of sample. So you will get concentration of sample into dilution factor, or alternatively you can find out the slope. Okay, so equation of straight line is y is equal to mx, y area of sample, x concentration of sample, m slope. So you know the area of sample, so x is equal to what? Y upon m. Y is say 330. So you have calculated the slope. Suppose it is, I will take it as a. So A. So you will get x, say milligram per ml. So you can use the slope method and you can calculate the concentration of sample. So the point is that the HPLC method of analysis, it is the method of analysis of the complex material. When material is complex in nature, the HPLC is used. Why? We get simultaneous separation and the quantitative analysis. If you see in the other methods, we have to separate the sample one by manual method and then we have to analyze. And if you said APC tablet and you have to analyze by volumetric method, it will take nearly 2 to 3 days for one chemist. But with the help of HPLC method, it is the physical method, no chemical reaction and anything, physical method only. And you have the availability of HPLC equipment within 1 hour with calibration curve method. Since 5 to 7 minutes are sufficient to run one chromatogram, so within maximum 2 hours, the whole sample is analyzed accurately. So time is saved, cost is saved, and the analysis becomes very fast. In the industry, sometimes I have worked in the industry, and what happens? In the industry, on one side the production is going on and you have only 10 minutes to 30 minutes to give your results. Since production is going on and it is correct or not, you have to approve by the quality control chemist. एका बाजूला प्रोडक्शन चाललेलं आहे आणि ते प्रोडक्शन बरोबर चाललंय किंवा नाही चाललं, पॅरासिटामॉल टॅबलेटचं कॅफिनची कंटेंट, ॲस्पिरिनची कंटेंट बरोबर आहे किंवा नाही, हा तुम्हाला अर्ध्या तासात किंवा 1 तासात रिपोर्ट द्यायचा आहे. कारण तोपर्यंत प्रोडक्शन थांबलेलं असणार. ट्रायल घेतली जाते अगोदर. फर्स्ट ट्रायल इज टेकन and the trial tablet is analyzed. Okay, once it is okay, the production is continuously taking on. In between, okay, when production is going on, analysis is also carried out. So in the industry, sometimes it is the requirement, whatever the technique used for the analysis should be very fast, and this requirement is fulfilled by the HPLC. So if you see in the pharmaceutical industry today, analytical method development and validation, new drug discovery, HPLC and HPLC connected with EMS. This is not the suitable time, okay, since EMS is the separate topic, MS is the separate topic. But with normal HPLC, how qualitative and the quantitative analysis is can be carried out are discussed here. Okay, so with this I'm going to finish my lecture. Okay, if anybody has doubt, if you have difficulties, you can ask.
Thank you so much, sir, for such a wonderful lecture. It's very good lecture. So, at the end of the program, I request to Dr. Nirmala Kakade ma'am, convener of this webinar, to express vote of thanks.
Namaskar. Today, Department of Chemistry and IQAC of Dadapatil Rajale College organized national level webinar on HPLC technique in pharmaceutical and chemical industries. Really, we experienced a very great and enthralling lecture. In the beginning, I am sincerely thankful to our patron, Honorable Appasaheb Rajale alias Kaka, head of our institution. I am very thankful to Honorable MLA Monika Tai Rajale, Honorable Trustee Rahul Dada Rajale, Honorable Shivajirao Rajale alias Tatya, Chairman College Development Committee, and Honorable Secretary J.R. Pawar Sahib. I would like to express my deep gratitude towards today's resource person, Honorable Dr. D.R. Shinde sir, Professor Ramkrishna More College, Akurdi, Pune, for sharing such informative and novel ideas and thoughts with us. On behalf of our institute, our college, our department, and IQAC, thank you, sir. Thank you very much. I will thank respected Dr. R.J. Temkar, sir, Principal, Dadapatil Rajale College, for his continuous support and valuable guidance. I am also thankful to OS Vikram Rao Rajale, sir. I express my thanks towards Dr. M.S. Tambori, in charge Arts Faculty, Dr. J.N. Nehul, in charge Science Faculty, Dr. S.J. Deshmukh, in charge Commerce Faculty, and Professor C.N. Pansare, in charge Computer Faculty. I am also thankful to IQAC Coordinator, Professor R.T. Gholap, and Assistant Coordinator, Dr. Atul Kumar Chorpagar. I am thankful to all the teachers from Dadapatil Rajale Junior and Senior College and Professor Ravindra Kishore Phalke from Technical Department. I am thankful to Dr. Sadhna Mhaske, Professor Aslam Shaikh, and all my colleagues. I am very thankful to all the students and participants who attended this webinar very sincerely. By the permission of authority, I announce the program is over. Thank you very much.